Hello everyone, welcome to Brain Blitz Audios. Today in this episode of NEET preparation, we'll be looking at previous year questions of physics in medical entrance examinations in India. Today we're dealing with a very important chapter, which is alternating current. This is the 7th chapter in the grade 12 syllabus for physics in CBSE. And when we look at alternating current, this is one of the most sought after chapters in grade 12, and a lot of questions have come based on this chapter. So this chapter is very, very important. What's more important is that this episode has a very important question at the end of this video. So stick around and watch the whole video. Let's move on to our first question, asked in AIMS 2008. An AC source of angular frequency omega is fed across a resistor R and a capacitor C in series. The current registered is I. If now the frequency of source is changed to omega by 3, but maintaining the same voltage, the current in the circuit is found to be halved. Calculate the ratio of reactance to resistance at the original frequency omega. How do we solve this question? In the question, it is given that at frequency omega, an AC source has an RMS value of current, and it will be equal to VRMS divided by Z. VRMS stands for root mean square value of voltage, and Z stands for the impedance, because over here we have a resistor and a capacitor. So the reactance that is from the capacitor and the resistor that is showing resistance both combine together to form a value known as impedance, which resists the flow of current. Now, the current registered is I for this case. Let's find out the value of Z, which is known as impedance. For an RC circuit, there will be a resistance and a capacitive reactance, also known as XC. The formula for impedance will be XC the whole square plus R square, which is both of them under a root. So the value of IRMS is equal to VRMS divided by XC square plus R square the whole root. Now, what is the value of XC, or capacitive reactance? It is equal to 1 by C omega. C stands for capacitance, omega stands for the given angular frequency. So we can write IRMS as VRMS divided by under root of R square plus 1 by C omega the whole square. This is our first equation. The next condition is that if the frequency is changed to omega by 3, now the angular frequency will be omega by 3, the current in the circuit is found to be halved. So therefore, at frequency omega by 3, the value of the current will be IRMS divided by 2, which will be equal to VRMS divided by R square plus capacitive reactance here will be 1 by C into omega by 3, which is equal to 3 by C omega. R square plus 3 by C omega the whole square, both of that under a root. So this is the value, this is our equation number 2, and this is the value of the capacitive reactance, XC, in this situation. So now we have two equations. The next thing that we do is divide both the equations. So divide equation 1 by equation 2. So therefore, it'll be IRMS divided by IRMS by 2. And the right-hand side will be equal to VRMS divided by under root of R square plus 1 by C omega the whole square divided by the RMS, the whole divided by under root of R square plus 3 by C omega, the whole square, which we can write as R square plus 3 by C omega, the whole square, divided by R square plus 1 by C omega, the whole square, all of that under a root. Basically, what happens is we cancel out VRMS, so it will be 1 by under root of R square plus 1 by C omega square, whole divided by under root of 1 by under root of R square plus 3 by C omega, the whole square. So it's 1 by and 1 by, so their positions get switched, and it will be of the form R square plus 3 by C omega, the whole square, divided by R square plus 1 by C omega, the whole square, everything under a root. So this is the value of IRMS divided by IRMS by 2. The left-hand side will now become 2 because if you cancel IRMS, it will be 1 divided by 1 by 2, which is 2. 2 is equal to R square plus 3 by C omega, the whole square, divided by R square plus 1 by C omega, the whole square, under root. Now what we do is we square both sides. When we square on both sides, we get 4 is equal to R square plus 9 by C omega, the whole C omega square, divided by R square plus 1 by C omega square. We take this denominator to the left-hand side, so it becomes 4 times the denominator, so that becomes 4R square plus 4 by C omega square is equal to R square plus 9 by C omega squared. What we now do is we rearrange the terms of this equation. So therefore, we get 4R square minus R square is equal to 9 minus 4 divided by C omega, the whole square. So now it's 3R square equals 5 divided by C omega whole square. We'll put R square to the right-hand side, 5 to the left-hand side. So basically it's cross multiplication. So what we get is 3 by 5 equals 1 by R into C omega, 1 by R square into C omega square. Basically, we can write this part of the equation, the right-hand side, as 1 by C omega. Okay, let's write it over here. 1 by C omega divided by R. So therefore, it becomes XC square divided by R square, because 1 by C omega is capacitive reactance and R is resistance. So therefore, now we have XC square divided by R square is equal to 3 by 5. So when we take square root on both sides, we will get XC divided by R is equal to under root of 3 by 5. And this is our answer because we're asked to find out the relation between the capacitive reactance and the resistance at the original frequency, omega. And our answer is now option A, root of 3 by 5. And to find that out, we use the RMS value for both current and voltage. Then we found out the value of the impedance. This is for both cases at omega and omega by 3. Then we divided both the equations in order to get a relation between XC by R, XC and R. So XC divided by R now becomes under root of 3 divided by 5. And that is option A. Let's move on to the next question. If an AC main supply is given to be 220 volts, the average EMF during a positive half cycle will be option A 198, option B 220, option C 240, option D 220. So in an AC main supply, the value of voltage as well as current will be the root mean square value. So the value that is given in an AC main supply that is written on it is the root mean square value of the given quantity. So therefore, if an AC main supply has 220 volts written on it, then VRMS is equal to 220 volts. And the formula for an RMS value of both voltage and current will be equal to the average value divided by root 2. So VRMS will be equal to V naught by root 2. If it's IRMS, then it will be equal to I naught divided by root 2. So let's plug in the value for VRMS. So V naught divided by root 2 is equal to 220 volts. V naught is equal to 220 root 2 volts. Now, our question is to find out the average EMF during a positive half cycle. How do you find the average EMF during one positive half cycle? We use the formula 2 by pi into V naught. So this is the formula for the average EMF during one positive half cycle. 2 by pi is 2 by 3.14 into the value of V naught, which is 220 root 2. When you divide 2 by 3.14, you get a constant value of 0.63. And then we have 220, and the value for root 2 is 1.41. Now what we do is we convert this to whole values. So 0.63 is 63 by 100 times 220 times 141 divided by 100. This is the value for average EMF. So now we have 63 times 141 times 220 divided by 10,000. So what do we do next? Let's multiply 141 and 63. This should be easy. 1 times 3 is 3, 4 times 3 is 12, 1 times 3 is 3, 3 plus 1 is 4. 1 times 6 is 6, 4 times 6 is 24, 1 times 6 is 6, 6 plus 2 is 8. So now we have 3, 8, 8, 8 on addition. And we're dividing this value by 10,000, so we'll get 0.8883, which we can write as 0.89. So all of this quantities will now culminate into 0.89. And then we have the voltage, 220. So here we have more multiplication. So let's multiply 220 times 89. 0, 18, 18 plus 1, 19. 0, 16, 16 plus 1, 17. So we have 0, we have 8. Now we have 15. 1 comes over. 2 plus 7 is 9. And there is a 1. And since there is a decimal point for 2 places, let's add it over here, 2 places to the left. There it is. So the value of the average EMF during a positive half cycle is 195.80, which using approximation, we can write it as 196 volts. So the value that we get is 196 volts. But remember, for getting this value, we have approximated the value of pi. So there's always an amount of variation possible. So we have got the value 196 volts experimentally. If we look at our following options, we can see that option A, 198 volts, is the closest value to 196 volts. So therefore, the right answer is, in fact, option A, which is 198 volts. That depends on the value of pi and the value of root 2, both of which are irrational numbers going over vast decimal places. So that is how we find out the average EMF during a positive half cycle. This formula is very important. 2 by pi times the average EMF. Next question. A coil has an inductance of 0.7 Henry and it is joined in series with a resistance of 220 ohms. So therefore we have an LR circuit. When the alternating EMF of 220 volts at 50 hertz is applied to it, then the phase through which current lags behind the applied EMF and Wattless component of current will be respectively. So these, we need to find both the phase difference and the Wattless component of current. And we have the following options: 30 degrees, 1 amperes, 45 degrees, 0.5 amperes, 60 degrees, 1.5 amperes, none of the above. How do we solve this question? The value for L is 0.7 Henry. The value for R is 220 ohms. The value for E naught, or alternating EMF, is 220 volts. And the frequency of alternation is 50 hertz. And remember, we're dealing with an LR circuit. So when we have an LR circuit, if the current is flowing along x-axis, then the voltage of the inductor is actually perpendicular to the current by a phase difference of pi by 2. It leads the current, while the component of the EMF of a resistor is always in phase with the current. So VL and VR are perpendicular to each other. Similarly, we can say for their resistances. So XL will be perpendicular to R. And to find the resultant, which is the impedance, we just add both of them together like that. So R, then XL, and then there is R square plus XL square, the whole root. And this value here, the angle of the resultant, is the phase difference phi. In order to find the phase difference, what we do is we use trigonometry. Tan of the phase difference, that is tan phi, is equal to opposite divided by adjacent. So XL divided by R. So now XL divided by R is our ratio. What is XL? XL is the inductive reactance, which has the value L omega. Inductance times the angular frequency. And the formula for angular frequency is 2 pi times the linear frequency, which is given. So we have L into 2 pi nu divided by R. There's always a component for resistance at the bottom because it's a ratio. So L omega is XL and R stands for the resistance. And omega becomes 2 pi times nu. So now let's move on to solving this question. So tan phi, this is equal to 2 times pi. Let's take it as 22 by 7 for the sake of calculation. Nu, the frequency is 50 hertz, and 0.7 will be the amount of inductance because L was given as 0.7 Henry, divided by the resistance, which is 220 ohms. So over here, 7 times 1 is 7. So 7 times 0.1 will be 0.7. So we can cancel those out. We have 0.1. And then 2 times 22 will give you 44. 50 times 0.1 is equal to 50 into 1 by 10. So 50 by 10, that is equal to 5. The whole divided by 220 ohms. Now at this stage, we usually try to cancel, but then if you know the multiplication of 44 times 5, which I'm doing here right now, so 20 plus 2, 22. So as you can see, both the numerator and the denominator is 220 in the end. So therefore, the value of tan phi is equal to 1. So the value of phi is tan inverse of 1, which is equal to 45 degrees, which we can write it as pi by 4. 45 degrees is the value of the phase difference. So if we go back here, we find that 45 degrees is the answer. So just by that, we can identify our right option. But then if it wasn't so simple, then we would have to go towards the Wattless component of current. So for the sake of understanding, let's do the Wattless current as well. Again, once you find out the phase difference, then the Wattless current is a piece of cake. The formula for Wattless current is I0 times sine phi. I0 is the average value of the current which is given. Now, I0 can be written down as V0 divided by the impedance Z. So therefore, we can write V0 divided by Z times sine phi. The value for sine phi is sine 45. Sine 45 is 1 by root 2. So V0 by Z into 1 by root 2 is now our Wattless current. Let's plug in the values for V0. V0, we can write it as E0 as well. So that's just the alternating EMF. The value is 220 divided by Z. The formula for Z in an LR circuit is XL square plus R square, the whole root, into 1 by root 2. Now remember that we got the value of inductance, which is the numerator, as 220. And the value for resistance was already 220 as it was given in the question. So the numerator here for tan phi, which is 220, is the value for XL. Tan phi still remains XL divided by R. It's for the sake of simplicity that we plugged in the values for L and for frequency and then calculated it. So now we know that the value of XL is 220, the whole square, plus the value for resistance, which is again 220, that is also under a square. Both of these terms under a big root, into 1 by root 2. So now what we do is I take 220 outside the root. 220 inside the root, it will be just 1 plus 1 into 1 by root 2. 220 gets canceled. So now we have 1 by 2. So the value for Wattless current is equal to 0.5 amperes. If we go back to our option B that we marked as the correct one, the value for Wattless current is 0.5, and the value for the phase difference is pi by 4, which is 45 degrees. So therefore, by calculating both the phase difference and the Wattless component, we have succeeded in telling that option B is the right option. And we did that using calculations. Now let's look at the next question. An inductor and a resistor are in series. So this is again an LR circuit question. They are connected to an AC supply of a variable frequency. We don't know the EMF. We don't know the frequency. The question is, as the frequency of the source is increased, the phase angle between current and the potential difference across the inductor will decrease, increase, and then decrease, decrease, and then increase, go on decreasing, go on increasing. So how do we solve this question? We again use that ratio. We had XL, we had resistance. The value for impedance is XL square plus R square under root. So if we have a phase difference phi here, then the value of tan phi is equal to XL divided by R. Once again, the formula for XL is L omega. So L omega divided by R. And the value for omega is 2 pi nu divided by R. This is for tan phi. So now notice that tan phi is directly proportional to the frequency, the linear frequency of the circuit, the LR circuit. So therefore, as tan phi increases, the value of frequency also increases, and vice versa. So if we are able to increase the frequency of the source, then we are also able to increase the tangent ratio of the phase difference phi. And if we draw the graph for tan, you notice that from 0 to pi by 2, the graph is increasing. Now, that means that as tan phi increases, the value of phi also increases. And the value of tan pi by 2 is infinity, so that's the maximum that anything can reach. So if tan phi is up to infinity, then phi reaches pi by 2. So the maximum value of tan phi gives you a phase difference of pi by 2. So therefore, as tan phi increases due to the increase in frequency, the phase angle between current and the potential difference across L will go on increasing. So that means option D is the right option. The trick here is to find the relation between tan phi and frequency. And since we know using the graph that tan phi reaches its maximum value at pi by 2 and its least value is at 0, so therefore there is an increase in the phase angle. So as tan phi increases, the phase angle phi also increases. So therefore, when the frequency is increased, the tangent ratio of phi is increased. So that means phi also gets increased. Option D is the right option. Let's look at this question. In an AC circuit, the voltage and current are described by the formulae given below. V is equal to 200 sine 319t minus pi by 6 volts, and I is equal to 50 sine 314t plus pi by 6 milliamperes, respectively. Our question is to find out the average power dissipated. The first equation is of the form V is equal to V naught sine omega t minus phi. Let's consider this as phi 2. And I, the current, is I naught sine omega t plus phi. Let's consider that as phi 1. So the value for phi 1 is pi by 6. The value of phi 2 is minus pi by 6. And the value for V naught is 200. The value for I naught is 50. And then in order to find the actual phase difference phi, we just subtract the values. So phi 1 minus phi 2. So therefore, minus pi by, it's pi by 6 minus of minus pi by 6, which becomes pi by 6 plus pi by 6. So therefore, pi by 3 is the phase difference. So we have all of what we need in order to calculate the average power dissipated. The average power dissipated, P0, is equal to Vrms times IRms times the power factor, which is cos phi. Vrms is V0 by root 2 times IRms is I0 by root 2 times cos phi. When you multiply that, it becomes V0 I0 divided by 2 times cos phi. So this is the formula that we'll be using. Let's plug in the values. So P0 is equal to the average value of the EMF is 200 times the average value of current is 50. But in this equation, the unit is in milliamperes. So I0 is 50 milliamperes. 1 milliampere is 10 raised to minus 3 amperes. So 50 milliamperes will be 50 into 10 raised to minus 3 amperes. The whole divided by 2 times the value of phi is pi by 3. So cos of phi is cos of pi by 3. So now, how do we solve this question? Let's divide 200 by 2. So you'll get 100 times 50 into 10 raised to minus 3 is the same as 5 into 10 raised to minus 2. And therefore, we have cos pi by 3 on the right hand side as well. Cos pi by 3 has a value of 1 by 2. Pi by 3 is 60 degrees. Cos 60 is 1 by 2. So 1 by 2. Now, we could divide 100 by 2, but the easier way to go is the 10 raised to minus 2 will cancel out 100, which is 10 raised to 2. 10 raised to 2 into 10 raised to minus 2 is equal to 10 raised to 2 minus 2. 10 raised to 0, that is 1. So we have 5 divided by 2 watts as our answer. Let's divide it. 5 by 2 is easy. It's just 2.5. So 2.5 watts is our average power for this AC circuit. So therefore, option A, 2.5 watts, is the right answer. We use the formula P0 is equal to Vrms times IRms times the power factor, which is cos phi, where phi is the phase difference. And we got the value P0 is equal to 2.5 watts. This is our final question for this episode. If we decrease the frequency of the applied alternating current with a purely capacitive load, 1. The amplitude of VC, 2. The amplitude of IC, whether both of these values increase, decrease, or remain the same. You need to find that out. And we have 4 options regarding the condition of both of these quantities. Now, this question is asked in AIMS 2011. And the way to go about this question is simple, but it requires some sort of tricks. The first trick to note is that the amplitude of VC is not dependent on the linear frequency of the AC source. So therefore, the amplitude of VC remains unchanged if we decrease or increase the frequency of the applied alternating current. So therefore, 1 always has to be the same. If we analyze our options, we can immediately discard the options A and D because they say that that the amplitude of VC either increases or decreases, both of which are incorrect. By analyzing those two options, we can also note that the amplitude of the current passing through the capacitor is dependent on the linear frequency, because both of the options marked same are wiped out. So how do we find out this relation? Well, it's simple, because what we do is we just use Ohm's law. Instead of the resistance, what we're using is the capacitive reactance. So IC, I is equal to V divided by Z, which is XC in this case. So that is VC times C omega, because XC is 1 by C omega. So VC divided by 1 by C omega is VC times C omega. And then once again, omega is 2 pi times nu. So as you can see, IC is proportional to the linear frequency. So as the frequency increases, the current also increases. So therefore, the right answer is option B, as the 1 remains the same, 2 increases. That concludes this episode of NEET preparation. We hope you found this interesting and very informative. For more of questions regarding the chapter Alternating Current or any of our physics lectures, don't forget to click the link in the description down below, where you can enjoy and get more information regarding these important chapters. For watching more of our useful and interesting content, don't forget to subscribe to our channel, which is Brain Blitz Audios. We have uploaded a lot of content at Brain Blitz Audios, and we have some of their links in the description down below, which includes NEET preparation. So don't forget to click the links and watch them. Until the next webisode, take care, stay safe, bye-bye for now.